astronomers have detected more than 5,000 planets orbiting other stars. New space telescopes, exploiting aggressive new technologies, and backed by artificial intelligence, are expected to multiply this bounty at least tenfold. There could be trillions of planets in our Milky Way galaxy alone. Are any of these alien worlds alive? Are living creatures common in the cosmos, or rare? These are some of the most challenging questions science has ever faced. Clues to the answers may be found in the early universe, but they are hard to see because space itself is relentlessly expanding. The light from those early times has been stretching, shifting further and further down the spectrum into the red. To probe events that far back in time, astronomers must search with sensitive infrared detectors, like those aboard the James Webb Space Telescope, or JWST. Because Earth itself generates heat, these instruments must be placed far away in the cold of space and extensively shielded with their backs to the sun. Based on the Hubble Space Telescope Deep Field surveys, astrophysicists think they have a rudimentary model of how the universe formed. But the Hubble can only see back to a point about 500 million years after the Big Bang. And it lacks a spectrograph to identify which elements existed and when. The Webb Telescope could surprise them with details from only 50 million years since the beginning of time. It's not known why, for example, when the universe was just 5% its present age, there appears to be a sudden firestorm of star formation. Clumps of hydrogen gas quickly draw together, heat up, and ignite the fires of fusion. The cosmic sunrise, some astronomers have called it. It takes less than 2 billion years for the first galaxies to form. The JWST can examine more than 100 at once. These young galaxies are small and disorganized, but they are populated with very large stars, perhaps 10,000 times more massive than the Sun. Burning hot and fast, these early megastars will not last. The most massive stars are likely to collapse and explode as supernovae, creating and delivering the heavier elements needed for life. But if a big star explodes in a small galaxy, its more complex atoms may be driven beyond that galaxy's gravitational power to haul them back. Our vast Milky Way galaxy, of some 400 billion stars, has enough mass to retain the rich chemistry needed for life. Our galaxy births, on average, about 10 new stars each year. The more massive a star, the hotter it gets. The faster it uses up its hydrogen, and the sooner it will burn itself out. Astronomers classify stars by their surface temperatures, which governs their colors. Big blue O-type stars, like Alnitak in Orion's belt, can be up to 100 times more massive than our Sun, burning up to 15,000 times brighter. But they will die in less than 30 million years. White type A stars, like Sirius, the brightest star seen in the skies of Earth, are about twice as massive as our Sun. They can live up to 2 billion years, long enough for life to arise on their planets, but, based on Earth's history, not long enough to develop intelligence. Once begun on a planet, life probably needs a relatively smaller star to help it evolve, one that is stable and not stormy. A star like our Sun. We are living proof of what's possible. Our parent star is in the middle of its 10 billion year life, clearly time enough for the happy accidents of evolution to build a world like ours. Astronomers would like to find other bright yellow mid-sized G-type stars, but less than 5% of the stars in our Milky Way galaxy are Sun sisters. Cooler, lower-mass red dwarfs, the M-type stars, live much longer than ours. It is easier to detect Earth-mass planets that may be tugging on these small stars because the telltale wobbles in their stars' positions on the sky are proportionally greater. There are also many more red dwarfs than yellow suns. 3/4 of the stars in our galaxy may be these small M-type stars. Under their cool red glow, their planets would be twilight worlds. Creatures there might well develop larger eyes than ours, more sensitive to longer wavelengths. With more time to evolve and more niches to survive in, it's tempting to imagine that these smaller, cooler stars could offer better odds of life. But to be warm enough for liquid water, planets around red dwarfs must orbit close in, running a greater risk of radiation from flares. Many red dwarfs suffer roiling surfaces and tempestuous star spots. Even smaller, cooler stars lurk in the shadows. Infrared stars, also known as brown dwarfs, range between 15 and 70 times the mass of Jupiter, not quite massive enough to sustain nuclear fusion. Orbiting infrared telescopes are finding them in surprisingly high numbers. This tells astronomers that the galaxy has no problem making small objects. But brown dwarfs are not planets. Gas giant planets may be only a fraction of the mass of a brown dwarf star, but they generate strong electrical fields and dangerous radiation. It is thought unlikely that life could develop close to a gas giant unless somehow shielded from its lethal energy. Big, puffy worlds like these also tend not to concentrate important heavy elements like iron, potassium, sulfur, oxygen that are needed for biology. nor do they form oceans of water or pleasant atmospheres. If gas giants have solid surfaces at all, they are buried deep in the thick, cloudy atmosphere, never exposed to their star's light. So far, Earth is the only known living planet. It is dangerous to reason based on only one example, but it seems most likely that life would prosper on a relatively small, dense world like ours. Though we don't yet know how life got its start on Earth, most theories revolve around abundant liquid water set in motion by strong tidal forces and an active atmosphere that stir an ever-changing broth of compounds, giving chemistry the chance to boot up biology. At some distance from every star lies a region at just the right temperature for water to remain liquid for millions of years. Around hotter stars, this band of temperature is wider and further away. Around cooler stars, closer and tighter. In this so-called habitable zone, a planet might sustain life as we know it. Astronomers have at least 15 different ways of spotting exoplanets. So far, most have been detected by a slight drop in the brightness of light as the planet passes in front of the parent star, as seen from the vicinity of Earth. This is called the transit method. Astronomers have confirmed many planetary systems with more than one planet in the habitable zone of their stars. This particular system has 3 and is a promising early target for the James Webb Space Telescope. The whole system is tiny, revolving around a very cool star named TRAPPIST-1, which is not much bigger than our own planet Jupiter. All 7 planets orbit within a zone smaller than the orbit of Mercury, our innermost planet. Using the Webb to compare their atmospheres may give scientists a roadmap to detecting life in many other systems. These 7 planets affect one another's orbits. In a few such systems, the planets' gravitational interactions have pulled them into a stable, resonant ballet. They come closest together at regular repeated intervals, recurrently exchanging their momentum to keep the timing constant, like a precisely built clock. Truly, music of the spheres. This exchange of energy can warm these little worlds, encouraging chemical reactions as tides incite their fluids to mix. It is possible that life could arise on even smaller objects. In 2021, astronomers using the ALMA Array radio telescope detected a disk of material swirling around PDS 70c, a massive exoplanet 400 light-years away. It was the first observation of moons caught in the act of forming around a planet. Once built, such moons can hold deep subsurface oceans beneath protective shells of ice. Exactly this is happening within our own solar system. Jupiter's 4 largest moons, the ones discovered by Galileo in 1610, flex and tremble due to tidal gravity. Ganymede, Callisto, and especially Europa are nearly certain to host subsurface oceans. Saturn's huge moon, Titan, and tiny Enceladus Each contain a liquid sea beneath their crusts. In February 2005, the Cassini mission first began picking up evidence of salty water spewing from large cracks in the icy surface of Enceladus. These could be snow globe worlds. Deep within the oceans of Earth, oases of life have been discovered. These lush ecosystems don't require sunlight. They draw energy and nutrients from hot water gushing through fissures in the seabed, driven by our planet's molten interior. A similar alien undersea realm on a nearby moon or a distant exoplanet may await discovery. It is difficult to imagine how such a detection could be made without sending a probe. There are plans to try just that in our own solar system. Stars, however, are almost unimaginably far apart. It's not yet practical to send spacecraft to even the very nearest ones. Fortunately, astronomers have come up with ways to gather clues to life from afar. If the orbit of an exoplanet crosses the face of its star, starlight filtering through that planet's atmosphere can disclose its makeup, element by element. In 2001, the Hubble Space Telescope identified hydrogen, oxygen, carbon monoxide, and sodium in the high, hot clouds of a giant world named Osiris. Later analyses found water vapor, methane, and carbon dioxide. Osiris is likely too hot, too dry, and too close to its star to host life. But this detection sparked the quest for biomarkers, molecules in the atmospheres of exoplanets, which could be the exhalations of life. Operating at longer wavelengths than the Hubble, the new James Webb and Nancy Grace Roman space telescopes can determine chemical composition more clearly. The shifting balance between methane, carbon dioxide, and oxygen can point to the developmental stage of a planet's biology. Planets are also brighter in the infrared than in visible light, while stars are dimmer. Infrared detectors can see through clouds of interstellar dust and penetrate the local star soot emitted by the parent suns of exoplanets. By deploying a star shade, future space telescopes could simulate an eclipse of a parent star, blocking enough starlight to determine an exoplanet's overall color, and perhaps taking direct photos of its surface and atmosphere. What astronomers are looking for are signatures of change. On our amazing planet, primitive plant life dramatically altered the atmosphere, consuming carbon dioxide and releasing oxygen, poisoning an earlier generation of microbes, making conditions hospitable for an explosive diversity of more complex life. On today's Earth, scientists are finding living organisms nearly everywhere they look. Among the nearby stars, nothing astronomers have found so far suggests that our solar system or our homeworld must be unique or special. Researchers are now confident there are at least 10 billion potentially habitable Earth-sized planets in our galaxy, which is only one of at least 50 billion other galaxies. Perhaps the range of life in the universe, on planets, within moons, inside asteroids, or elsewhere, is greater than we've dared imagine.